I'm going to talk about materials in the flatland. So I'm Konstantin Novoselov I'm a professor of condensed matter physics. I lifted it from a recent letter I received from China. So I'm a professor of condensed matter physics, School of Physics and Astrology. And first, I got a little bit offended, but then I thought that's probably what I should do in my talk today. So let me spend half of the talk on physics, and then half of the talk on astrology, trying to predict the future for graphene and for the 2D materials, etc. All right, so some of you probably already realized that I lifted the title for my talk, not my title, the title for the talk from the famous book of Edwin Abbott-Habit, the Flatland, and same as the book itself, I will have two chapters, two parts in my talk. First, the flatland, our world, the two-dimensional world, and then we will try to make a connection to the real world, to the three-dimensional world, in either terms, in terms of the three-dimensional materials and in terms of the real applications. So why graphene? So since it has been obtained for the first time, people realize a number of unique properties of this material. It's, of course, the thinnest possible, it's the strongest possible, the most impermeable, the most conductive, thermally conductive, and so on. And I always try to bring attention of people that the most important property here are those 3 points at the bottom, because we keep coming with the new, very attractive properties of this material every now and then. And it's quite surprising, because really what is graphene is just assembly of carbon atoms in two-dimensional manner on a plane in a hexagonal structure, only carbon, nothing else, and yet it has so many superlatives concentrated in one material. Well, it's a simple hexagonal structure, but in fact, if you ask a physicist, it's not that simple. In fact, it has a property that you cannot replicate it with one single atom. You always need to replicate two atoms. So I colored them red and green. Of course, in reality, we all know that the carbon atoms are blue. But because there are two of them, you always need to think about superposition for electron. It has a chance to sit either on one or on another. In the quantum mechanical world, it sits on both simultaneously, and then it gives us the very special band structure, electronic band structure, which has this conical shape, and well, there is lots of physics associated with this. I don't want to go too much into details, into all the equations. I think you had enough. So let me try to demonstrate what is so special about this linear dispersion relation. Well, just to give you a couple of cartoons, most of the conductive material in our world can be divided into two classes. Those where electrons conduct electricity and those where holes conduct electricity. Negatively charged quasi-particles or positively charged quasi-particles. If you want an analogy to real world, it's like having a country with single party system, like Russia or North Korea, and then those electrons are people, represented by people, and they are free to move within the country without any problem. But if you bring the two countries together, you form a border control in between. You can't control the flow of people through. And that's exactly how modern electronics work. You take two materials, one is electron-like, one is hole-like, bring them together, you create a border control, and you can control the flow of electrons, electric current. So that's the basic, that's modern electronics in a nutshell. Graphene is very much different because electrons and holes are described by the same equation, by the same wave function, and that's why the good example for graphene would be United States, where you can have the state can be either Republican or Democratic, but still people can cross the border between states without any problems. So, and that's why electrons in graphene can propagate without scattering on very long distances. That's why it has very high conductivity, and that's why people try to use it for high-frequency electronics, high-performance photodetectors, and so on. I mean, I can go with the physics examples more and more. Quite surprisingly, if you just take 2 layers of graphene, it would behave completely different. The quasi-particles are described by some really bizarre equation, but I don't have an example of a country for that, so I won't be talking about that material today. So, as I said, this property of that electrons can go without scattering through any border gives very high electronic properties to graphene. We usually indicate it in terms of a number called, a value called mobility, and to give you a benchmark for the typical silicon transistor, which is in your laptops, is 1,000 centimeters square volt second. For the best HEMT devices, which are in your mobile phones, maybe it's about 50,000. And in graphene, we get into more than 1 million at low temperature, probably 1 million at room temperature as well. So we're doing really, really good. There are problems associated with this, linear dispersion relation, which also can be seen as a relativistic property. And it's very exciting physics there. It limits our ability to use it for transistor application, but I will tell you later how we can overcome this issue. Another interesting property is the optical properties of graphene. You can think about what kind of optical properties one layer of atoms can have. I have millions of atoms between me and you, and I can see perfectly what would one extra layer do. Apparently, quite a lot. It absorbs quite a sizable fraction of light, namely 2.3%. So that's the picture of a graphene sheet over here. That's nothing here, and you can see there is a slight contrast in between, and it's 2.3%, as I said. But surprising fact for physicists is that this number is actually given only by the combination of the fundamental constants. It's pi times alpha. Do it at home, 3.14 divided by 137. Alpha is the most fundamental constant of this universe, is the fine structure constant, which determines the interaction between matter and light. And so basically, if you ever forget what is fine structure constant, you look at graphene, divide the contrast by pi, and you get this most fundamental constant of the universe. And of course, this 2.3% is actually quite easy to measure for a physicist. It's quite a lot for us, but for device engineer, it's really a negligible number, because people would kill to have a material which is as conductive as graphene and would absorb only a tiny fraction of light, like 2.3%, which a good example, and that it would go as a heart in many applications like touch panels and solar cells, LCD displays, and so on, everywhere where you need conductive but transparent material. Here is an example where we made graphene LCD display, and indeed you can pinch off the optical transmission, and we use graphene as a transparent and conductive coating here, which tells us that applications with graphene are quite realistic, and let me spend a few minutes on the possible applications. What is actually good about graphene is that it has, of course, a number of those superlatives, so it can try to substitute many materials in many applications. But what we like about graphene, that we can possibly invent completely new applications which were not possible without graphene at all, which would use a number of the unique properties of graphene altogether. So there is one example. We can now grow large areas of graphene, and we can use graphene for switchable contact lenses, for example. You take a contact lens, you put graphene on top, you take another one, graphene, fill in the gap with liquid crystal material, and then if you apply voltage to it, it can change the optical power. So you don't need to carry many glasses with you. You just have one smart contact lens, and you change power, and you change the voltage on this contact lens, and you change the optical power. Another example, because graphene is so impermeable, it can serve as a very thin corrosion protection layer. So that's copper partly covered with graphene. It's oxidized everywhere, part where graphene is covering it. Or we can make it tunable. We can make the permeation of different molecules tunable in this material, and we can use it for filtration or maybe desalination purposes if we treat graphene in a special way. Those membrane applications are actually quite appealing because it can be used a lot in biology. If you think about this, biology is it's all about membranes, which atoms or which molecules can penetrate through, which cannot, and then you can mimic the function of the membrane, of the biological membrane with the artificial material. And of course, University of Manchester is uniquely positioned because we have a huge, very strong expertise on the life science part of the campus. So there is a lot of work on the biological properties of those of graphene membranes. So for some time, although the application seems to be realistic, there was a problem. Can we actually grow? Can we produce enough graphene? Because the LCD cell which I showed you, it was 30 microns across. And of course, if you don't want a TV which is 30 microns across, you want something which is 30-inch across. And before we'll go to how we solved this issue of graphene production, let me tell you a story about the production of graphite. Because there are some properties, some type of graphene which are produced from graphite as a starting material. The reason why I want to tell this story is that because the birthplace of graphite is actually only a few hundred miles from here. It's in a place called Seathwaite in the Borrowdale Valley. It's close to Keswick in the Lake District. Very picturesque place. You can go to those mines, and you can still collect some graphite there. So the first mention of graphite is actually this date is wrong, is 1555 in the Royal Papers, and already 1565 we see the first mention of graphitic pencil, which was made from Borrowdale graphite in the book of Conrad Gassner, published in Zurich in the year of his death. So it really spread across Europe extremely fast, probably even faster than graphene did. People realized the strategic importance of graphite, and they just artificially inflated the price for it. So the price for a pound of graphite in the beginning of 17th century was one pound sterling, and at that time a pound was like three-week wages for the miners. So it really created a huge problem with the illegal access to the mines and stealing of graphite. And then they even had to introduce a special law special legislation through the parliament about the illegal access to the mines. And the punishment was public whipping and hard labor for 1 year. And I always tell our students that this law is still enforced in our lab. If you touch graphene, you are condemned for 3 years of hard labor as a PhD, and then public whipping at your viva. The very title of this slide, the black market, that they say that it actually originated from the illegal market of graphite, which existed in 17th, 18th century Britain. So it's not my idea. I stole it from the Keswick Pencil Museum. So these days, there is fairly legal gray market of graphene. And one of the first companies which started to operate there was opened by one of my PhD students, Peter Blake. And they started to sell graphene at some ridiculous price, £1 per square micron. I mean, square micron, so your hair is 100 microns across, so it's 10,000 square microns. So it's really some strange price. The reason for that was that our first samples were really tiny, just a few microns across, so they could barely afford the postage expenses, but then we learned to produce better and better samples these days. Millimeter size or even larger are not a problem. And of course, if you extrapolate the price, you would get you would have to charge people some ridiculous amount. The good thing about that is that we now moved from flake production into really the proper mass production of graphene, depending on, so you probably know that some of the first samples were produced by the Scotch tape method. We actually still use it in the lab up to now. But depending on the price and the quality you want to achieve, there are many possible ways how to produce graphene. From liquid phase exfoliation, you basically get inks, to CVD methods, which you get monolayer graphene, to many other methods as well. So let me now switch gears now and go to the second part of my talk, to the two-dimensional, from the 2 dimensions to 3 dimensions, to our world, to the spaceland as it is in the flatland. So, and here I probably start with National Graphene Institute, and I would like to tell you a story about NGI as well. So that's how it looks now. You can go and take a look. It's close to aquatic center. That's how it looked about 2 years ago when we started archaeological survey on this on the premises. We were quite excited to undig the rows of 1780s, 1820 terrace houses from the beginning of Industrial Revolution in Manchester. But also we noticed the remains of a fairly large building over here, which was identified as an Albert clubhouse. And we probably won't know much about this building, but this gentleman was the member of this Albert clubhouse. And it was basically a public club for German expats in Manchester in the beginning of Industrial Revolution. It's Engels, of course, and since every single building on the university premises has to be named after a famous Mancunian, we immediately came, I maybe stupidly came with the idea that we should be, NGI should be called the Engels building. And we tried to bring the parallels between Industrial Revolution, graphene development, and so on. And when we communicated it to George Osborne and David Willits, the science minister at the time, and of course it was very naive on my behalf. They said that, Kostya, we give you money to do research, not to explore communist past. And we were waiting for the general election. It didn't happen. So, but I mean, NGI still doesn't have a name, right, Nancy? So it's still free. So we still, who knows, with the Brexit, we might have another chance for the Engels building. But similarly, as the Communist Manifesto wasn't written by Engels alone, we're not going to concentrate only on graphene. We actually study many other materials in the NGI. And that's what we call beyond graphene. So now we have this fantastic building, and our students are, of course, very always bright eyes, bushy tails. They keep asking me, because you spent 60 million on the building, can we afford to buy not only the lead pencil, can we afford to buy some other colors as well? Well, in principle, yes, there are some money left. We can buy a pack or two, and apparently it happened to be that if you exfoliate other materials, you can come with other materials which are only 1 atom thick, but they would have a very different properties from graphene, and what even more interesting, they would have very different properties from their 3-dimensional counterparts as well, and collectively they cover a huge range of properties. Say boron nitride is a good insulator, niobium diselenide is a superconductor. moly is a semiconductor. So collectively, we have a huge range of properties in this new class of materials, the two-dimensional atomic crystals. And that really gives us a very interesting opportunity in material engineering. Let me give you a little bit of the background. If you think about it, there are only a few materials which determine our world. Like all electronics is silicon, construction is mainly steel, aerospace engineering, it's aluminum, a little bit of titanium. And the fact that only a few materials really determine our world, they also introduce huge restrictions of what we can do. If an engineer wants to create a new transistor, first thing he has to do is to check what's the band gap of silicon, what's the band gap of silicon oxide, and then work within those restrictions to create new devices. Ideally, however, we want to mix and match the properties of different materials to fit it into the particular application we want to achieve. And that's what we call composite materials or heterostructures. And in principle, those examples already do exist, like plastics or composite materials. But those examples are still few and far between. And of course, ideally, what you want is to be able to design a new material from scratch by atom by atom, or at least layer by layer engineering, and then you can specify the functionality of each layer according to your needs. Like the top layer would be my sensor, the next one would be my solar cell, then interconnect, some logic, and then within a few layers, you have a new material which has the functionality built in its own structure. And with the appearance of the 2D materials, 2D crystals, we have this possibility, because when I come to the lab, I have those materials as a library available to me. And what I can do, I can start combining them together in a three-dimensional stack. And then I basically encode every single layer with whatever properties I want, and I can create and code whatever functionality I want. So those examples already do exist. So that's already what 2-3 years ago. Thanasis was laughing that it's just a ghost from the past. He's fully commercial now, but it was one of his PhD papers. So you can make, so those 6 layers would make a good transistor, and that's so those few layers would make a solar cell, and indeed we can combine. And it's still 6 layers of atoms, so really nothing more. So we can really create new functionality or even mixed functionality in very, very thin layers. Surprisingly, the quality of those crystals are extremely good. I know it's probably beyond the scope of this talk, but I still want to show you how we see it and how amazing is the technology now. You can take this heterostructure. I won't go into details what it is, so it has a purpose. And we can kill it, and we can cut a piece out of it, like a rectangle like this, and we can take it, this very, very thin rectangle, and look through it, and we can see all the individual layers there, and then you see those individual layers, those individual atoms, and you see the boron nitride, graphene, then boron nitride, and graphene again. Here is even better example. We started with a layer of boron nitride, and then we put 2 layers of graphene, then 2 layers of boron nitride, then 2 more layers of graphene, 2 more layers of boron nitride, and 2 more layers of graphene. So it wasn't done to bore you to death. It had actually a function. It's a resonant tunneling transistor. Again, so, but if you look, especially in the dark field, you won't tell me where the boron nitride stops and where the graphene starts. So the quality how we can assemble it is extremely high. So now let me spend the last maybe 10 minutes of my presentation telling you a little bit more about the possible applications. So those heterostructures, they look amazing, and they are amazing even even for me. The fact that you can assemble with the atomic precision something of so many layers just looks unbelievable. But it's still a matter of few years before we would be able to grow it in large quantities. Well, what can we offer now? Well, one of the ways how to produce graphene, I told you, is the liquid phase exfoliation. You basically shake graphite in the right liquid, and then you create an ink from graphene. And you can print with this ink if you want. But then the same trick can be played with the other materials. So we can have an insulating ink, or we can have semiconducting ink. And basically, we just put those inks into the inkjet printer, and we can start printing the same heterostructures I showed you before. And so it's literally you just print with those inks, and then you can print whatever functionality you want. So here is the solar cell, and indeed it does work, and it reacts on the gate. So it's not very high quality, but for the fact that you simply come with 3 cans of paint, and then you paint them one on top of another, and then you have your wall be acting as a solar cell. It's quite appealing. So here is the one example of the device which already works, and it's completely commercial, so it's being sold now. You can print RFID antenna. RFID is the sort of device which is in your proximity contactless credit card. So inside there is an antenna and a chip, and usually this antenna is made from copper, which is expensive and not very convenient. We can print it. We can print it on paper. We can print it on anything, working in any frequency range. And what is really my pride is that we start to use other materials in it. Some of those antennae require an insulating layer, and we can print boron nitride inks there as well. So now before we go to the final part of this talk, just to tell you how good is our antenna, let me again, for the 5th time now, tell you a story. So the story takes us back to the Second World War. Britain was, sorry, I drew those pictures a week ago in US, being just struggling from the jet lag, so don't judge me on those, please. And so the Second World War, Britain bombs Germany, Germany bombs Britain. Both sides utilize radars to detect the foreign airplanes, and of course, if they are detected, it's quite easy to be hit. So what Britain pilots did, they used the so-called chuffs. It's basically strips of metal. They throw them from the airplane, and then it basically blinds the radar. The problem is that it started long before Turing cracked the Enigma code, so UK is still within the blockade. There is not much aluminium available, so people were charged with creation of something conductive and something cheap. So, and here is a story. I'm really thankful to Robin Idle, who told me this story. They decided to replace aluminum stripes with graphite ink. So here is the story. So that's how it looks. Here is the story as they gave it. So within 24 hours of the first report, by working right through the night, some 15 samples of different inks has been prepared. Then 2 most promising samples were made in large quantity in a cask within a few days. That's now where graphene is coming through. There is always an issue how well you can print, and you still need very low resistance. So they say the 3 flakes that overlap acts best. So that's basically, they came with this idea of graphene long time ago. the typical plot from a chemist, no units at all, but we can get something from it. And it's just amazing. Within 2 weeks, the mills were in full production and many hundreds of tons of window material were produced. Now, for these guys, it took 2 years to produce printable ink. So that's just, that story really amazes me. But still, it's a commercial product. In the university, we're trying to go beyond that. So we're trying to link those RFIDs with some useful sensor applications. So you don't only transmit the information which is stored in the chip, but which is also acquired from the environment. So it can say what's the temperature in the room, or you put a carton of milk into the fridge, the milk turns sour, the pH sensor signals to the fridge, it went bad, go and get another carton of milk. Or we can even try to put a combined sensor in one device. And here's an example of such a sensor. Of course, you know that the University of Manchester has also a very strong school on materials, also on textile. We also created graphene textile, which is sensitive to a number of things, to temperature, to humidity, to strain, to electric field. So we basically coat every single strand of that yarn with graphene, and then you can use it for the textile. And here is an example how it works. So that's the antenna printed from graphene. That piece is the graphene yarn, and so this antenna, it doesn't have any batteries. It's just really, it's a piece of paper basically. And then you can you basically can sense temperature with it. So if you heat it up with the heat gun, so the temperature goes up, and you can read it wirelessly on the computer. It's even better because it's extremely sensitive. So here we have you don't even need a heat gun. You just put your finger next to it. Just really, the heat from your finger is enough and you can detect it easily. So I hope I just guided you through from the physics of graphene, which is still exciting, to the possible applications, and the number of those applications still grows day by day. And of course, there are many more now available through the appearance of the other 2D materials, and hopefully will be even more with the heterostructures. And what is left for me to do is to thank my collaborators, Andrew Gaiman, all the active PhD students and postdocs in our lab. Thank you so much.